So we're going to look at derivatives of logarithmic functions. And so our goal at the end of the day is to uncover why the derivative of the natural logarithm of x function equals the function 1 over x. And this is true on the domain for the natural log function, so this is true whenever x is greater than 0. Now to see why, all we have to do is remind ourselves of the relationship between the logarithm function and the exponential function. Let g of x be the name we give for this function natural log x. This should tell us that e raised to the g of x is equal to e to the natural logarithm of x, and we know that e raised to the logarithm of something should give us back just x. So we have this equation, e raised to the g of x is equal to x. Now when I have two functions that are equal, it so happens their derivatives are equal. So I'm going to compute the derivative of both sides of this equation using the rules of derivatives that I know. Well, on the left-hand side, I have e raised to a function. So using that generalized exponential rule, the chain rule for exponentials, it should be e raised to the g of x multiplied by the derivative of that exponent g of x. Whereas on the right, the derivative of x is just the constant function 1. Now remember, what we want to know is the derivative of g, because g is representing natural log x. If I divide both sides of the equation by e to the g of x, then what I get is that g prime is 1 over e to the g, or, returning to my relationship here, I see that g prime is 1 over x. So we have that the derivative of the natural logarithm function is, in fact, 1 over x. So we have that if we look at the function natural logarithm of x, which remember passed through this point 1 comma 0 and had a vertical asymptote at x equals 0, then from the fact that we know that its derivative is 1 over x, we notice that the function 1 over x is always positive, so this reinforces the fact that ln x will increase because its derivative is greater than 0. We also then can see that if we look at the second derivative of the natural logarithm of x function, so if we take the derivative of ln x, we get the derivative of 1 over x, which is negative 1 over x squared. And that is a function which is always less than 0. So the second derivative is negative, tells us that this function is in fact concave down, and we can see that from the graph. So now we can use the fact that we know the derivative of the natural logarithm of x function being 1 over x to find the derivatives of functions that involve it. We could look at the function f of x equals x natural log x, and by this I mean the function that is the product of the function x with the natural logarithm of x function. And since this is a product, we're going to use our product rule. So we have our first portion here, I'll call that function a, the second portion b. So my function a is x and its derivative therefore is 1. My function b is the natural logarithm of x. Its derivative is 1 over x. So I can obtain f prime is the derivative of the first function times the second plus the derivative of the second function times the first, which would be 1 times natural log x plus 1 over x times x, and that's just ln x. And if I do 1 over x times x, I'm left with 1. Here's a second example. Let's suppose we look at the function f of x equals 3 natural log x over x squared plus 4. To obtain the derivative of this function, I'm going to use the quotient rule. So I'm going to consider my top function to be the 3 ln x. My bottom function is the x squared plus 4. The derivative of the top by the constant multiple rule should be 3 times the derivative of natural log x, so 3 times 1 over x, and the derivative of the denominator is 2x. So putting this together in my quotient rule, I'll have the derivative of the numerator, 3 times 1 over x, or 3 over x, times the denominator left alone, minus derivative of the denominator, 2x, times the numerator, all divided by x squared plus 4 squared, the denominator squared. So let's now consider derivatives of logarithmic functions using the chain rule. So what we're getting at is trying to find the derivative of functions of the form natural log of some g of x. So I'm taking the natural logarithm of a function g of x, that's the function I care about. And the question is, what should this be? We recall that for a generic function, f of g of x, the derivative should be differentiating that outer function as g of x, its inside being the argument, and then multiplying by the derivative of that inside function. So if we do that in the context of this logarithm applied to a function example, we know the derivative of the natural logarithm of x would have just been 1 over x. So when we let g of x be the argument, the derivative will be 1 over g of x. But then I multiply by the fact that it's not just x, but a function of x, which was my argument. And so I get that the derivative of the natural logarithm applied to a function is 1 over that function times the derivative of that function. Pretty cool, huh? So let's just do 2 examples. So for our first example, let's look at f of x equals the natural logarithm of the quantity 9x plus 3x squared minus 2. So here my inner function, that g of x, is this part here. And so to obtain f prime, it should be 1 over the argument of the logarithm times the derivative of that argument, which therefore is 1 over 9x plus 3x squared minus 2 multiplied by the function 9 plus 6x, the derivative of that inside. And often we'll compress that, write it tidier, just by multiplying as 9 plus 6x, the derivative of the inside of the original function, over the original function's inside itself. For our second example, h of x equals e to the 3x minus the natural logarithm of the cube root of x plus 2 over 4x plus 1. So in order to obtain h prime, we're going to have to take the derivative of each portion. The derivative of e to the 3x would be itself times the derivative of that exponent. And then to do the derivative of the natural logarithm of a function, it should be 1 over whatever was inside. So 1 over the cube root of x plus 2 divided by 4x plus 1. But then that has to get multiplied by the derivative of that part that was inside the logarithm. So in the first bit, this isn't hard. We get e to the 3x times 3. In the second part here, I have 1 over a fraction, which makes it the reciprocal of that fraction. And then I'm going to multiply by, I'm just going to apply the quotient rule for that inner function to get the answer there. So 1/3 x to the negative 2/3 times my old denominator. I multiply by the evaluation of the quotient rule for the part inside. So the denominator being 4x plus 1 squared, the numerator would be 1/3 x to the negative 2/3, that's the derivative of the cube root of x, times the denominator, minus the derivative of the denominator, which is 4, times the numerator left alone. Lastly, a note. Sometimes we can use properties of the natural logarithm function to make taking derivatives easier. So by this in particular, I mean the fact that we know that the natural logarithm of the product of two quantities is the sum of their logarithms. And we also know that the natural logarithm of a number raised to a power, if that base is positive, should be that power times the natural logarithm of the base. So if I'm given an example like this, f of x equals natural logarithm of 4x cubed e to the x, before I take the derivative of that function, I could expand it using logarithms. The natural log of the first piece plus the natural log of the second piece in the product plus the natural log of the third piece in the product. And then that simplifies. Natural log of 4 is just a number, so that'll stay the same, but when I take the natural log of x cubed, that's the same as 3 times the natural logarithm of x. And then the natural logarithm of e to the x by inverse properties should just be x. So now, if I'm going to find f prime, rather than having to do the logarithm of a product, I actually can just take the logarithm of the sum. The derivative of log 4 plus the derivative of 3 natural logarithm x plus the derivative of just x. Since natural logarithm 4 is a number, its derivative is 0, because it's like looking at the constant function that evaluates always with the number natural log of 4. Then 3 natural log x would just be 3 times 1 over x, and the derivative of x would be 1. And so we get this very simple 3 over x plus 1 as the derivative of that function.